Happy day, friends. We are here for our last class on the second to last week. So just by way of reminder here, like I said before, we've got a PLC, which is just kind of a review. I put some review problems up. Just answered two of those. I called it the semifinal, which I thought was a pretty good name. Let's see, homework 7 I'm going to post a little bit later today. But that's today for me, and that means Thursday, because that's what day it is when I'm doing this. Final is going to be held on the 20th, which is a Wednesday. It's in fact 2 weeks from yesterday. Is that correct? Yes, because yesterday was May 6th, today is May 7th. So the final is going to be comprehensive and will be on the 20th. As with all other celebrations, it will be available to you during the day from midnight to 11:59. And so avail yourself of a good time slot and some good stable internet. As always, the usual things I would suggest. Make sure that you're set to go, right frame of mind, good quiet place, all the good stuff, usual things. Anyways, we're going to go ahead and keep moving on here. I'm going to start talking about the Bohr atom today. The Bohr model is something that you may well have heard of if you have taken, for example, a chemistry class or something like that, where they try to do an introduction to this, and I mean they probably get some of the things right, but ultimately the deeper understanding belongs to us. So Bohr's model of hydrogen came about in approximately 13. He started thinking about it in about 1912 and 1913. And it was basically pushed forwards by Rutherford's experiment, which happened in 1911. All right, so we're talking about 1913 here. And in 1911 was the Rutherford experiment. Now this is a hallmark experiment. Essentially, what happens is Rutherford is attempting to discern what an atom is more or less made of. And so he's doing that by shooting stuff at it. Okay, so is it at that point? Thomson had come up with an idea where that like an atom was like a big jello, and if there were bits of stuff in here, like the electrons and electrons and protons were just kind of scattered around in here. It's known as the plum pudding model, where charge was positive charge was effectively smeared out. Okay, but these things here were negative electrons. Because Thomson knew that the electron was a particular, it was a discrete particle, all right? He had already found that essentially any element could emit electrons when, for example, heated, okay, or bombarded. So electrons come flying out. So he knew that electrons were in atoms, in every one of them, and that they were particles. He just didn't know what the atom looked like. So he kind of thought that one way it might happen is these electrons are bound in to a positively charged, kind of smeared out jello. Like that, and they're all bound together, right? So that when he heats up something like this, positive charge doesn't come out, but it kind of helps the electrons jiggle a little bit more and then get ejected. Okay? This is known as the plum pudding model because Thomson was English, and there is a dessert, I guess you'd call it. It's around the holidays, known as the plum pudding. Usually it is soaked in brandy, and that definitely helps with that time of year. And then you light it on fire. And also, if you're really lucky, there might be a couple of coins in there that you can. It's like lucky to get a slice of the plum pudding and then have there's a tuppence in here or something like that, right? So anyway, this is what the plum pudding model looked like. Rutherford decided, I want to find out. If I shoot stuff, like if I shoot fast-moving, large in the sense that a nucleus of helium is considered large when you're thinking about an electron, right? I'm going to shoot these things in at it. They're fast-moving, they're relatively massive, right? And if this is what it looks like, then that thing's just going to tear right through, right? It's going to tear. There's not going to be anything else except you're going to detect everything over here, right? And it might even be slowed down a little bit by all this jello it's got to go through. Well, this is not exactly. He found mostly that, but that's not everything he found. So Rutherford decided to thin out a foil of gold. Right? Pounded it so it was very, very thin. Gold, of course, being extremely heavy. And then at the gold, he shot what are called alpha particles. The alpha particle is, like I said, the nucleus of helium. So it's 2 protons, 2 neutrons. Obviously, we know that now. He didn't really know what they were. They were just things that he could somehow make and shoot and make them go fast. He didn't know that that's what they were. Otherwise, this experiment would never have been needed, right? The point is that these things, when you give them a lot of kinetic energy, act like pretty fast-moving, like a Volkswagen, right? Bam, a Beetle. And inside the gold are parked a bunch of dump trucks. Okay, so imagine elastic collisions between a Volkswagen coming in really fast and hitting a dump truck. Okay, but those dump trucks are parked pretty far away from each other. Right? Right? You're not as we know now, the atom is in fact mostly empty space. So having an alpha particle hit one of those, a nucleus-to-nucleus collision is really rare, right? You have to do a lot of push through and just kind of wait a long time for these things to hit. So what he found was eventually, right, the alpha particles being positively charged are coming in here and being affected by the positive charge of the gold nuclei. So you can find that they might be swerved upwards a little bit, right? Or if they come in like this, if they come in right here, right, they might be swerved up quite a bit. Or, and this was a real crazy thing, if they hit almost flush, and this is, by the way, super rare, they come straight back like this. And that was the thing Rutherford could not ignore. If you are firing something like this, and it's hitting, well, if it's hitting something like this, there's no possibility of something like this happening. This recoil is amazing. Okay? And he described his surprise at finding something out here, finding the alphas hidden out here. He described it as if he's firing these big, huge, like battleship guns, right, at a piece of tissue paper, and they're hitting and bouncing off, right? That's how he thought of the alpha particle, big, huge, kind of like bullets, shooting at something which seems to be extremely flimsy, but in fact hits something that is extremely massive, extremely dense, and recoils completely off. Right. Now, this establishes the nucleus. This establishes that a nucleus is a very heavy piece of the atom, and in fact, the atom is kind of built around the nucleus. Right? So that's what the upshot of this was. And Bohr basically took that and ran with it. Sorry about my voice today. I'm getting to that end of the semester, too much talking. Much better. Okay. All right, so this establishes the nucleus. Bohr is aware of this, and he decides to construct a model of hydrogen based on a nucleus with a planetary, like nucleus as the sun and planetary orbits as the electron orbits. Okay, so the Bohr model of hydrogen really looked like proton being massive, right? Knowing that the nucleus is composed of really heavy things. Well, come on now, you know what? Really heavy in relation to an electron, yeah, right? A proton's about 2,000 times more massive. Proton is kind of the sun. And the electrons as planets. Okay, and this is typically what you see when you look, when people draw an atom for you, right? There's a dot with a bunch of circles around it, or maybe like elliptical orbits, making it look kind of cool. Okay, this is based off the Bohr model. And the reason that that is still used is because it's an easy visualization technique. All right. When thinking about what the electrons do, he said, okay, if these were actual planets orbiting about the sun, you could have any orbit, right? We could move Earth over about 10 meters and then have basically an orbiting Earth that's 10 meters closer to the sun. Bohr said when it comes to an atom and the electrons orbiting, that cannot happen. And his justification for that was, it can't happen. Right? It's one of those things where he's just got to take a leap and go, well, this is not what we see. The reason that he says this is because he wanted to, in his mind, make the link between electrons moving between orbits and emitted light, photons that were emitted. Right? This is what the atomic spectrum is all about. Okay? So when you look at his hydrogen model, okay, that positive charge right there would be the proton, and then you'd have an electron that could move in an orbit like this. We'll call that the n equal to 1 orbit. And then there's another one out here. We'll call that the 2. Okay? Concentric circles. There's a 3. Etc., etc., etc. I'll draw the 4, because I should probably at least get a 4 in here. So we'll draw the 4. And so his hypothesis was electrons, well, okay, there's one electron in hydrogen, but it can orbit in one, if you help it up, it can go from, it's normally going to be in this state, but you can push it up into the 4 state and it'll drop back down. When it drops back down, it drops into particular orbits. Every time it drops into an orbit, below it, it emits light, right? That's where the photons go off. So, if I have a sample of hydrogen gas, and I have, 10 to the 23rd of these atoms in the gas, and I'm causing the electron to jump way up and then come down like this, you notice that there's a visible spectrum of light emitted by the gas. Okay? So this is known as the Balmer series because it's visible, and Balmer was the first one to try and put a mathematical formula behind it. All right, so Bohr's postulates were basically that electrons make jumps between orbits. There is no orbit that's between, right? An electron, according to Bohr, cannot exist, say, in there. Okay? There is no possibility for an electron to be in there because there's no stable orbit for it there. And the same would be true out here. Wherever there's not an orbit, the electron can't be there. So it jumps only between allowed orbits. Actually, allowed would be a great word to put right in there. Allowed. Allowed. So that so that it's not in orbit. And by the way, these orbits are integer numbers, so there's no 2.2, right? There's no 3.5, right? All right, whenever a jump is made, it requires a photon. If it's a jump up, you need to put a photon in. If it's a jump down, it's a photon emission. Okay, so we say that an electron that's up here in, for example, the 4 state. Okay, remember this is hydrogen, only one electron. If it suddenly jumps down to the 3 state, I drew to the 2 state, we'll go here. If it suddenly jumps down to the 2 state, it emits a photon, and that photon is related to the energy difference the electron experiences between the 4 and 2 orbits. Okay, now, remember, or don't remember and learn this for the first time, the electron is negative and the proton is positive. Therefore, there's an automatic attraction between these two things. Okay? There's an attraction between these two things. So, when the electron jumps from here to there, it's actually lowering its energy. The energy is becoming less, and that energy difference is now going out as a photon. Okay? So what we're having here is when this happens, what we say is the photon emitted, right, is going to be indicative of the energy difference between the 2 orbits. Right? So this is the emitted photon. And it has a particular energy. Right? We know that we can measure the wavelength of this and then therefore say, oh, we know what the wavelength. We can measure the wavelength and say that we know the wavelength. And we can calculate the energy. Okay? So the single photon emitted has a measurable wavelength, and therefore a particular energy that we can calculate. And that energy must be the difference between the two energy states, the two electron orbits. The energy of the photon would therefore be hc over lambda, and that should be the same as the difference in magnitude. It would be the same as the difference between the energy of the 2 state minus the energy of the 4 state. Okay. And this should equal like so. All right. Now, I was mentioning that Balmer had come up with a mathematical formula for describing the visible wavelengths of hydrogen when it's emitted. And Bohr saw that and realized that he could make this jump. He could say, wait a minute, I bet I can tell you that the energy difference of the electron orbits is the energy of the photon. And therefore, it's that wavelength that we're seeing. So it turns out that the Balmer series is the series of only visible. Okay, now, we often get stuck into this mentality that the only thing that matters is stuff we can see, because so much of our sensory input is through sight. So notice that this electron here in the 4 state could have jumped down to the 1 state, but that would not be visible. That would, as it turns out, that would be a UV photon. It has too much energy. The wavelength is too small, right? This energy difference from here to here is too big for us to be able to capture in our eyes. But this one is just right. Okay, the 4 to 2 transition is a good one. The 3 to 2 transition, also a good one. The 5 to 2, and it also turns out that the 6 to 2 is supposedly visible, but hardly anybody can ever see it because it's just so far over in the violet range. All right, so let's go here. All right, so I just want to, I have to say this because sometimes this is not the first time you've seen this, and the people who often try to teach this make a big deal out of this. This is great. This is really great work. This is a fantastic analysis. It is not complete, however. This is not the modern view of atoms. It's not a sun with planets going around. All right? This is not what the atom looks like, right? And I mean, of course, it's on board 3 dimensions, right? It'd be like concentric spheres. No, it's not. Okay? It's not at all like that. So I just want to point that out. All right. So let's take a look here at the Balmer series. Boy, I'm sorry. All right, so we'll go through and take a look at the Balmer series here. This is the set of emitted photons due to an electron dropping or jumping such that it ends at the n equals 2 state. So you can think about, if I had enough energy to take an electron which was in its ground state here at the n equals 1 and just pump it way up. Just boom, it's way up, it's way out, right? I could draw these things, and suppose I'm way over here. The electron would start dropping down, right? It would drop down. Every time it drops, it gives an emission. Who's to say it drops one by one by one? It doesn't have to. It could drop from here down to there. And that's what the Balmer is. It's a drop from here into the n equals 2 state. Okay? It turns out that the visible ones are, like I mentioned before, drops from the 6, 5, 4, and 3 states into the 2 state. All right? Now, how did Bohr link all of this together? Well, he first started by coming up with a way to represent the energy of the electron within the atom. And there was a lot of work that he did in this. Ultimately, he says that the energy of the electron in the atom at whatever n state it is, and there was a bunch of physical constants which turn out to give you a number which is equal to minus 13.6 electron volts divided by n squared. So that the n equals 1 state is a binding energy of 13.6 electron volts. And you can test that basically by using some form of the photoelectric effect, right? If I have a hydrogen atom and I put in 13.6 electron volts, then what I'm going to get out are electrons which are going to be ionized from the atom, okay? Now, because ultimately what is useful to know here is that whatever's true going down as the electron jumps down is also true on the way up. So if I wanted the electron to make a transition from n equals 1 to n equals 2, all I have to do is hit it with a photon of that energy and make sure it can get absorbed. And we're off and running. All right, so now we would have what's called an excited electron. Sorry, I'm just going to plug this in here. Okay, there we go. All right. Therefore, the photon energy which comes out, like I said, we know is hc over lambda. And that's really going to equal the delta in the energy of the electron. Okay? So, if we were writing out solid energy conservation, because it always gets to here and it gets to a point where I screw signs up, because you always know that the photon energy is positive, but the energy of the electron as it goes from here to here, the change in the energy is negative because it's going to a lower state, a lower energy state. So I always screw a sign up here. Let's do this. If I write it out from an energy conservation perspective, the initial energy would be, let's just take the electron in the 4 state, for example, right? It would be electron in the 4 state. So that would have energy E4. And then in the final state, when the electron is now in the 2 state, there's also a photon that has arisen. So that energy has become E2 plus hc over lambda. Now, it's weird, but this E2 is more negative than that E4. So, if I were to solve this, I would say E4 minus E2, which is going to give me a negative number, right? I would say E4 minus E2 is going to be equal to hc over lambda. This is a negative number, that's a negative number that's bigger, So see, it's okay because I'm subtracting, all right? Now if I do it this way and I put this in for here, right, my E4 is going to be minus 13.6 over 4 squared minus negative 13.6 over 2 squared. Okay, and that should actually work out because these negatives are going to become positive, and this is ultimately a bigger number than that. So you can call this delta in E. Sometimes it's nice to use a 2 index notation. Sometimes it's nice to say N, where there's an initial and a final. I don't tend to do that. I just tend to say it's N. All right, so you could consider this to be, for example, N initial, N final. All right. And so this was what Bohr did, and it turned out to be spectacularly successful. Let's suppose, now for an example of this, let's suppose that we have a wavelength emitted that we detected, not visible, but let's suppose that we had a wavelength detected, and we want to find out what orbits the electron went between. Okay. I will also say that I'm going to put in a bit of a plug here for our 4D class. Now, if you're local and you're interested in this type of thing, we have a specialized class dealing only with relativity and quantum mechanics over the course of the entire semester. And it will be offered in the fall. It is only offered every other fall. So this is an even year, 26. So next time after this will be fall of 28 when we teach it again next. So if you are local and you wish to, learn a little bit more about this crazy stuff, then feel free to sign up because I'll be teaching it, and I think that it's going to be a lot of fun. It typically is. So anyways, let's do this. Let's suppose that we have a Balmer series line and we've measured it, but it is not visible. And it has a wavelength of, let's say, 379 nanometers. Can we find what the orbit was the electron started at? Okay, because we know if it's a Balmer line, all Balmer series photons are due to an electron ending in the 2 state. Right? That's the criterion for the Balmer. It stops in that one. Right? It then eventually will go boop, and jump down to the 1 state. Yes, it will do that. But to be a Balmer, that's the 2 state where you end. Okay. So let's take a look at something like this, where basically this is unknown. Okay. We're going to have an HC over lambda. Sorry. I am sorry. Boy. It's just that right time. I got an HC over lambda. Now this I should know. I have the wavelength. I know it's Balmer, so I know the final. This is going to be minus 13.6 EVs times, I'm just going to factor this out and then pull the, whatever those things are, the n's, 1 over n initial squared minus 1 over 2 squared. Because that's we have to do. Is that what we want to do? Yes, that's what we want to do. Now, in order to shortcut this, gosh darn. Something's got me. All right. In order to shortcut this, you can factor the minus through and flip these around. And so I often will do that. And I will cheat by just doing this. Because then you don't have to worry about your minus sign so much. Solving for this, what are we looking at here? Well, I have to pull the 13.6 over, and then I'm going to flip-flop the initial over here, and I'm going to pull this over there. So it's going to ultimately be something like this. 1 over 2 squared minus this thing here. And then this, it has to be underneath here somewhere. I'm going to call this like I guess I better call it E1. E1 should go in there. All right, so if you do this, there's all sorts of great stuff that can happen. You can square root it and then flip it over. I'm not going to do a symbolic for this because we know ultimately that this is 1/4 minus 1240. Note that the way I've defined E1, this is a positive number now. This is EV nanometers, and lo and behold, here in the denominator, I've got 13.6 EV and 379 nanometers. So the units all go away, which they have to, right? You'd have to have, this is only a number that we're looking for. Okay, I'm ultimately not going to be subtracting a number from something with units. Okay, so let's take a quick look here. If we do this, then we're going to get 1240 divided by 13.6 and 379, and that's going to be 0.24. So I'm going to make that negative. I'm going to add 0.25. Oops, 0.25. All right, now we're going to flip that over. 1 over, oh crap. Looks like this is about the 10 state, is what I'm seeing here. I'm getting about 10. Obviously, there are decimal points involved. You're going to feel free to ignore those because there is, like I said, there is no 10.3. That uncertainty in the, or I don't know if uncertainty is the right word, but the difference from an integer is likely due to how well did I measure the wavelength? Is it 379? Is it 379.1 or 2? Or is it 378.9? So those small differences in the wavelength will make a big difference in, well, not big, but it will make a difference in how well this comes out to be an integer. All right, looks like that's a 10. I'm kind of surprised by that. All right, let's do another thing where we're going to calculate the visible wavelengths. Right, this is the calculation Bohr did when he first put forth his model in order to try and reproduce the known visible spectrum. All right, so in the Balmer series, we have for visible, they are wavelengths that were well known and they were measured, and we're talking like, gosh, 1900.
they were able to measure what the wavelength is for each one of these lines. So the visible wavelengths were at well, never mind what that is. But let's say here that there's 4 of them that we can see. So we're going to go n initial, 6, 5, 4, and 3, and we're going to do n final equal to 2. Let's actually see if we can calculate what the wavelengths are. All right. I particularly, because I'm weird, I always start from the energy conservation. There are easier things to do here. Now, there's a thing where you can just do the 1 over wavelength, and then I think this is known as the Rydberg constant for hydrogen, times 1 over n initial squared minus 1 over n final squared. And you can see that all that is it's the HC underneath the 13.6, okay? This is in EVs, and so we're gonna do the same exact thing. This is known as the Rydberg constant. And it has a particular value, something around, I believe, 1.097. And I think it's inverse nanometers. Let's see if that's right. That may not be right. Sorry, I know this is right, but I got to remember what the, I don't remember if there's an exponent on here, so hold on. All right, I'm going to do 1.097. I'm just going to go out on a limb here and say, what if this is right? I'm going to do 1 over the initial. So let's start with the 6. The 6 to 2, we would calculate that wavelength. Let's calculate that wavelength. All right, so let's do 1 over 36 minus 1 over, I've got this wrong. Why do I have this wrong? N initial. What did I do? See, I told you I was going to mess up the minus signs. This is going to be a negative. I've got these backwards. Darn it. See, you people need to correct me before I do something like that. Darn, that means, yeah, see, I screwed up. I screwed up because I forgot that minus sign. That should be a minus right there. Okay, fine. Let's put the minus right there then. Okay, fine. Thanks a lot. Let me just hang out here like that with a minus sign error. Can't believe you people. All right, we're not doing 1 over 36. We're doing 1 over 4. Dang. Let me just mess everything up like this. I'm going to multiply that by, what, 1.097? And then I'm going to do, damn it. Yeah, so I'm off by a factor of 100. So this is apparently not the right thing. You might want to just change this. This is 10 to the 2, 10 to the, oh, crap. Jiminy's. I want the answer to be 100 times bigger. So I guess this should be 10 to the minus 2. All right, let's try that again. Okay, so now I'm going to multiply by 1.097. I'm going to divide by 100. Okay, now I'm going to do 1 over that number. Yeah, got it. Okay, sorry, this is your corrected Rydberg constant. So this needs to be times 10 to the minus 2, right there. And 6 minus 2 is obviously complete baloney, unless I have a minus out here, or I can put the minus through here and do that. So I get a lambda here of about 410. 410 nanometers. This is exactly what I was talking about. This is barely on the edge of visible because, like I've been telling you, the visible spectrum is, rule of thumb, 400 to 700 nanometers. This is 410. It's really, really deep violet. Very difficult to actually see unless you are in a dark room and have been so for a very long time, which at that point in time, right? Today, we don't have time to do stuff like they were doing back then. When you look at Rutherford's experiment, how do you think they did that? With the thin, so first of all, they had to pound out gold, all right? First of all, you got to get your hands on gold. Okay, that's easier back then, 110 years ago, than it is today. Pound that out, put it up. How do you think he was shooting them and then detecting where these things landed? All right, here's how they did it. It was a dark room and it was surrounded by phosphorus. There was phosphorus, right? Glow in the dark stuff. So that when it gets hit by something, it leaves a little beep. It makes a little glowing circle, glowing dot right where the alpha would have hit it. So you sit in the dark room first for an hour. You can't take data. You're just getting your eyes accumulated to a basically very, very dark and very, very low energy light situation, okay? Because these alphas are ultimately small. They leave dots, but it's really hard to see them. So you're in this room and all you're doing is sitting there for an hour, and then they're running the experiment by shooting the alphas, and then you're basically just trying to unfocus your vision so that you can see a dot landing over here, or a dot landing over there, a dot landing over here. And you would do this for, I think you could only do it for about an hour or two at a time before you just were like, I can't see anything anymore, right? It's actually a great human experiment to find out how long can I keep somebody in the dark looking at very, very faint dots on a wall. And lo and behold, it's about an hour or two. Same with this. So they had time that we apparently don't have these days. We are short on time. But anyways, that's a discussion for another time. Let's calculate. Well, you know what? We can just calculate. I can just tell you, right? Because if I put in 5, 4, and 3 for this, I'm going to get out different wavelengths. The wavelengths I'm going to get out. So this is the 6 to 2. Note that the 6 to 2 is the highest energy transition of the electron. Therefore, it's the lowest wavelength photon that we get that's still visible. Okay. Then we're going to do the 5 to 2, and we're going to find that that's 434. We're going to do the 4 to 2 and the 3 to 2, and we're going to find that this one is, this is always the one I never quite remember. That's 656. 434, I think it's like 470. I can't quite remember. We could actually do the calculation. Maybe that'd be a good idea. So we're going to do, what are we going to do here? 1 over 4 minus 1 over 5. Times that, divided by 100. And now we're going to do 1 over that. Ooh, that does not look good. I messed something up. Oh, I did 1 over 5. It's 1 over 25. Way to go. Okay. 434 is the 5 to 2. Gosh, am I just that? Yeah, anyways. I think it's something like 470. I don't remember. I'll put a question mark here. I think it's like 470. Or maybe it's 510. It is whatever it is. Anyways, the point is that these are visible lines, and Bohr can reproduce the wavelengths with a physical idea of what's happening in the atom. That was the big step forwards here. Okay, that was the big step forwards. So After that, and we are not going to go into any of this, but after that, it becomes a situation of how do we make this better? This is ultimately only a model of hydrogen. There are, last I counted, like 100 elements. Okay, there's like 94, the naturally occurring, but that's about 100. What about all those? Problem occurs when you start with putting another electron in here. That messes everything up. Okay, now we're totally screwed. But what you can do, one of the fixes to making this a better and more general model came from Henry Moseley. And if you decide to take 4D in the fall, we will talk about the work done by Moseley. Moseley essentially created the modern periodic table by looking at elements that were multi-electron, but then assuming that all of the inner electrons kind of shielded the outer ones, right? So imagine I have an element like what? Aluminum. I think that's numbered like 13 or something, okay? So imagine I have aluminum. So electrons, 13. Protons, 13. If I look at the outermost electron, what if I look at electron number 13? It's way out here. The other 12 electrons are kind of within, right? They're between the 13th and the nucleus. What does that mean? It means that from this electron's perspective, all these 12 electrons are basically shielding the other 12 proton charges in the nucleus, and therefore it acts kind of like a hydrogen atom, right? So you can actually take that and see how well it works for multi-electron heavier elements, right? And there's a bunch of other fixes to this that we can talk about when we take 4D together, because I'm sure that many of you will want to do that. We can talk about the fixes up to this, but ultimately this is not a complete model. It's not a general model of an element. It's a specific model to hydrogen, okay? And it does not really translate well to other elements. You have to fix it. And they tried to, and they did. They did a pretty good job with it, by the way, until the more modern formulation came along, and that's due to Heisenberg and Schrodinger, all right? So let's talk about the more modern formulation. I mentioned Heisenberg, and we talked about the Heisenberg uncertainty principle last time. I realized I didn't do an example for you with that, so let me do that. The Heisenberg uncertainty principle was that, and this, by the way, is not exactly true. You will see it this way in most beginning textbooks, but as to what delta means, nobody really knows. The hardcore actual Heisenberg uncertainty principle is written in terms of standard deviations. These deltas are supposedly here to make us think of approximately within here, kind of like a range. When we write a measured quantity, often we'll write it as that. This would be an average or something like that. We write it this way. So if you're not talking about standard deviation and you're saying, well, it's between here and here, that's kind of what we're doing here. So you'll find many different formulations. There's at least 4 that I can think of as to what this inequality ends up as. I told you that it was like H over here. Because this is not the technical Heisenberg uncertainty principle, and these are not standard deviations, because we're not going to take the time to calculate standard deviations. We're just going to do approximates. You will also find this as 1/2 H. You will find it as H bar which is the same as h over 2 pi, and you will find it as 1/2 h bar. So there are many different formulations for this. Ultimately, the point here is that these things don't really have the meaning that we need. They don't have the specific meaning that we need in order to say it's exactly one of these, okay? It turns out when I do put the standard deviations in here, it equals that. That's the one that it's equal to. But if we're not doing standard deviations here, then this is really just an approximate calculation. And of all of these, it doesn't really matter, okay? It's gonna end up a small number, okay? It's 10 to the minus 34, really no matter how you cut it. Okay, so let me see if I can, let me see if I can think up a quick example here. So we're gonna go to Heisenberg. So we'll go to this and say, suppose that we have a small, say, ball bearing, right? And it's a ball bearing which has a mass of about 0.101 grams. Suppose that we know its position to within like 0.5 of a micron. Suppose that we know that its position is plus or minus 0.5 of a micron. All right, so the question now is, what is its uncertainty in velocities? Okay. Now, remember that the uncertainty principle deals with momentum, and that's why we're seeing a mass in here. Okay. So really, if I wanted to write this in terms of velocities, it would be something like m delta Vx greater than or equal to h, okay? Or h bar, or whatever you want. Apparently it doesn't matter. So what would be the minimum uncertainty in the velocity? When I'm saying this, I'm always talking about making this inequality equal to an equality. In other words, you're at the bare minimum of satisfying the uncertainty principle. What is the bare minimum of uncertainty in the velocity that I can imagine here? Well, this is a number which is about 6.6 times 10 to the minus 34, and that's going to be in joule seconds. I know this, and I know this, so the question is, what's that? And so we can just divide those over, m and delta x. And you'll see here, yeah, all right, we'll do it this way. The mass is 0.01 grams, but I have joules here. I'm going to need to put that in kilograms. So that's 10 milligrams. So we're going to go 10 to the minus 5 kilograms here. And delta x, oh yeah, 0.5 microns. 0.5 times 10 to the minus 6 meters. The question you might have is, does this actually come out in units of meters per second? Well, you can check that because the joule second is a Newton meter second, okay? Here I've got meters, so that's gone. Now I'm down to Newton seconds. And now I'm going to take a kilogram out of there. Meters per second squared, seconds. Yeah, indeed, it does come out to be meters per second. Just by order of magnitude calculations, which is really all I'm expecting on problems like this, I'm going to go ahead and say this is 0.5. So this is 5 times 10 to the minus 7. And make that a 7 right there and make this into a 5. 5 and 6.6 are close enough. I don't really need to worry that much about them. It's going to be about 1. And I'm going to get a 10 to the minus 12 here, which is going to come up and make that something like a 10 to the minus 22 meters per second. This is definitely not observable. We can measure down to about, I gave you this uncertainty position for a reason. That's pretty much the limit of our resolution of where things are, right? We can look at really tiny things, but as to where it is measurement wise, it's pretty difficult to get a good resolution on that. So typically within about 10 to the minus 6 meters, we can measure to a reasonable approximation as to it's within that. So that's going to be about what is going to be happening here with the velocity. But that is way past our resolution. There's no way we're going to get anywhere near that. So you would say that this is not limited by what its velocity is. It doesn't matter. You're way past the uncertainty here if you're just wondering what its velocity might be. What is its range of velocities? Well, if you're saying it's stationary, then basically what you're saying is it's somewhere between negative 1/2 of this number to positive 1/2 of this number around 0. Right? So the range of the velocities is 0 minus that to 0 plus that, and basically that's 0. So we should be pretty satisfied that if there's a stationary ball bearing, it's stationary, and we're not going to detect anything like this. But if we have an electron within an atom, things could change, right? What if we did the same thing, and I wanted to say, well, what's the uncertainty in the velocity of an electron within an atom, right? I do the same exact analysis here. I would just have different numbers. What about electron within an atom? Now, atoms typically, based on the Bohr analysis here, the radius of the first orbit is about a 20th of a nanometer. All right. So let's just kind of widen that out. Maybe say it's 0.1 of a nanometer, right? Let's just say it's about 0.1. Let's suppose we've got about 0.1 of a nanometer, and the electron mass we know. So let's see if we can figure out what's delta V in the sense of it. Minimum uncertainty, mass divided by delta X. Yeah, here's what I'm going to do. Sorry, I'm just taking a sec here because I don't really want to do this calculation. What I want to do is with relativistic numbers. Well, not that it's relativistic, but I want to use electron volts, right? So what I'm going to do is I'm going to multiply and divide c squared over c squared down here. That way I'm going to use mc squared for the rest mass of the electron. I'm going to take one of those c's and put it up here. I'm going to take the other one and put it underneath here, so it's going to give me a fraction of light speed, right? So I'm going to get hc over mc squared times delta x, and I'm going to get delta v over c, right? Approximately what is its uncertainty in velocity as a fraction of light speed? Okay, so we would get 1240 eV nanometers here. We'd have mc squared, which is 0.511 times 10 to the plus 6 EVs, and we'd have 0.1 nanometers. So you'd say, well, wait, shouldn't it be, if the radius is 0.1, shouldn't it be 0.2? Yeah, but as you can see, we're not really concerned about factors of 2 or pi or anything like that. So it's approximately this, so I'm just going to use that. So our delta in V over C, what's this going to be? So this is going to be nanometers and EVs all gone. This is 1.2 times 10 to the 3 which becomes 10 to the minus 3. And this is 0.5. This becomes 10 to the minus 2. And this is a factor of a half, which goes up here and makes that a 2. It's about 2 times 10 to the minus 2. Which means it's traveling, if you think about C is 3 times 10 to the 8th, you're into somewhere in 3 times 10 to the 6th. You're into the millions of meters per second here. That's the uncertainty in it, right? So that means we have a range of velocities whereby it could be anywhere from minus a million to plus a million meters per second, right? Thinking of C as about 10 to the 8 here. Right? I'm going to get about 10 to the 6 as my delta V when I multiply that over. So that's a big range, right? So once you start confining the quantum particles, you start noticing much bigger differences in these delta Vs versus something that's macroscopic like this. It's an actual BB. It looks small to us, right? 100th of a gram. It's this really tiny thing. Looks really small to us. Uncertainty doesn't even touch it. You got to be in this range to really find the uncertainty principle. Alrighty, well, we'll call that good for today. I want to put out this as a general announcement. After your lab projects from last week, I'm going to go through and take a look at those. But there will be no more lab activities. So as of this week and next week, there's no more lab. I need to get your kits back, all right? So please start figuring how you are going to return the lab kits. Please start shipping it or dropping it back off with Julia or something. Please start making an effort to return our lab kits so that we don't have to then buy a whole bunch of more stuff to make new lab kits, okay? So it costs us money if you don't return them. So please return them. We are having funding issues right now, and it would be just lovely if we could get them all back. All right, I will be sending out an email to this effect as a reminder. So please start making those efforts to submit the lab kits back to us. That would be much appreciated. In the meantime, since there's no lab this week, I won't see you on Friday. So I will come back and we will be back here on Tuesday of next week. Have a great weekend, folks. Take care of your mom. It's Mother's Day. And please let her know that she means a lot to you. Okay? Because ultimately, without her, you wouldn't be here. All right? Happy rest of your day. Happy great weekend. We'll see you next time.